Alright, this is Mr. Craig in part 3 of the buffer question. And you'll notice that this question is a little bit different than the previous two questions in that I have 3 parts. What I plan on doing in this question is I'm actually mixing the 2 solutions that I prepared in part 1 and part 2, and I'm going to place those in 2 separate beakers. So I'm going to pour the 2 solutions together, and then I'm going to pour that one solution into 2 separate beakers so I can answer part B and part C and show you how well this buffer solution works. Alright, let's go right to the math here. Alright, in part A, it says a mixture containing 0.3 molar benzoic acid and 0.45 molar potassium benzoate. And you'll notice in the ice chart, again, I have my ice chart set up so that I have my 2 concentrations that I formed in part A and part B. I had the hydrogen again at approximately 0 because there is some hydrogen in both of those solutions, but I want to find out what the hydrogen concentration is at equilibrium after these 2 have been mixed together. So to do that, I want to write my expression, and again the expression I'll use has hydrogen as a product, and I'm using a Ka value here. So again, you'll notice that I have the plus and minus x's, which is appropriate, but since we're using the 5% rule, we will eliminate those so that we now have this remaining in our expression. Solving for the hydrogen concentration, we'll rearrange the variables and have hydrogen separated and alone. So in this case here, we're solving for x, and x in this case happens to be the hydrogen ion concentration at equilibrium. So to find the pH, take that negative log of the hydrogen concentration, and in this reaction, or when the 2 solutions are brought together, we have a buffer solution that has a pH of 4.37. Now, when preparing buffer solutions, it's a good idea to know what you want your pH to be at, so you can, for whatever reason, you might have different experiments that are taking place, and you might need a buffer range in that certain pH, just like with your blood, how it has a certain pH, and your blood is also a buffer system and a very, very effective buffer solution. And what it does is it helps regulate the added hydrogen and hydroxides that we ingest from our diet and other things that take place in our life. So here's our pH of our 2 solutions mixed together. What I want to do now, forgot about the Henderson-Hasselbalch equation. So if you want to use that, that's also a quicker means. And again, it's the anion over the weak acid for our concentrations when plugging in there for the 4.37. Again, an option. If you wish to use the Henderson-Hasselbalch equation, it will save you a little bit of time. But you'll notice that you come up with the same answers here. Alright, in part B, what we're going to do now is we're going to take the solution that we prepared in part A and pour it into 2 separate beakers so I can have one beaker for part B and a second beaker for part C. And in part B, I'm adding a strong acid to the solution, the buffer solution, and I want to see how well the solution can manage the added hydrogen that was added to that. And you'll notice if you look back in question 1 and question 2 that those 2 solutions did not handle the hydrogen very well. Actually, B did handle it, absorbed all the hydrogen, but the pH was changed quite a bit. So, plugging in the values at the initial, okay, so we're adding the hydrogen in, and whichever of these 2 values is smaller goes to 0. So the hydrogen will go to 0, but equilibrium again, once again, will be reestablished, so we'll have some concentration for the hydrogen. And what I want you to do is, realizing that we have hydrogen on the product side, we're going to use a Ka value and our respective expression. So rearrange the variables so that you have the hydrogen isolated and all by itself, so we can calculate for the pH. So once we calculate for the pH, we notice that we have a pH value of 4.21. Alright, we'll talk about that pH here in a moment. Again, using the Henderson-Hasselbalch equation, great option if you know how to use it. Alright, so let's talk about how effective this buffer was, or if it is a good buffer at all. Well, one thing I want you to notice is that if we look at these before and after pHs. So I have a pH in part A of 4.37. That's before any acid was added to the solution. And then the pH after the acid was added to the solution. You'll notice that we have a change of about, we'll say roughly 0.16. And that's not bad. Again, we're adding a significant amount of hydrogen ion to this solution. And if you look at question 1 and question 2, you'll notice that the pH really changed by a lot in part B, not so much in part A because we were adding an acid to an acid. Now, I would consider this to be a good buffer solution. The reason why is because there is not a very large change in pH. So this solution was able to absorb the hydrogen, part 1, and the pH was kept in check for the most part. Not a bad scenario there. Alright, part C. Just to show that a solution, a good buffer solution, can absorb either hydrogen or hydroxide, I want to compare its pH. So one thing I want you to notice right off the bat is that we're adding a strong base to this buffer solution, and that any buffer can handle the addition of a strong acid or a strong base. But when setting up your ice chart, keep it respective. What I mean by that is, make sure that you have your hydroxide or your hydrogen on the product side. You'll notice in the equation that I have written up here, yeah, I agree. I have hydroxide on the reactant side. But to keep myself out of trouble when writing the expression and not getting the inverse of the answer or getting some really crazy pH or pOH value at the end, I'm going to go ahead to help myself and put the OH or the hydroxide, or I'm sorry, the OH or the hydrogen on the product side. And do notice that I have the strong base with the weak acid. And in the previous step, or previous part, I have the strong acid with the conjugate base. We never put acids with acids and bases with bases. You can, but as you saw in question 1, it's not a very good system at absorbing hydrogen or hydroxide. So we want to put the hydrogen, which would be considered our acid, with our base. So down here in the OH, I'm putting the hydroxide with my weak acid to have this desired reaction. Alright, again, we need to use a KB expression since we have hydroxide. Rearrange the variables so we can get our hydroxide concentration at equilibrium. So we'll do the rearrangement there. And then we get our hydroxide concentration. Ooh, hold on, something happened there. We get our hydroxide concentration to be 3.53 times 10 to the negative 10. Finding out what the pOH is from that, we get 9.45, and our final pH is 4.55. Talk about that here in a moment. One thing I want you to notice here, when using the Henderson-Hasselbalch equation, you'll notice that I'm going straight to the pH and using the pKa and using the log of the anion over the weak acid. That is legal. If you know what the pKa value is, which we do, we know the Ka value. It's 6.45 times 10 to the negative 5. And if we know what the anion, or the more negative charge is, we can use this. So if I come up to my ice chart and I look over here and find out which of these two, and again I'm comparing my common ion with my weak acid. These are the only two things that I consider when doing the Henderson-Hasselbalch, is the common ion and the weak acid, or the weak base and its common ion. So which one of these is more negative? Well, there it is. So whatever that concentration is, the 0.52, will go on top. And then whatever the concentration, and again that's at equilibrium, and whatever the concentration of my weak acid is, will go on the bottom. So even though I have hydroxide in my equation and I solve for the pOH up here, I can go straight into it and solve for what the pH is. And I'd highly recommend that, if you know how to use the Henderson-Hasselbalch equation. Now, coming down here, looking at this, is this a good buffer? In my opinion, the answer is yes. The reason why it's a good buffer is because, again, it resisted a large change in pH. Adding a significant amount of hydroxide to the solution, yes, it did change it by about 0.24, but again, it's still within that nice range. So, this again goes to show how a good buffer works. I hope this helped.